Bismillah Rahman Rahim. In this session, we will discuss pressure from O-level physics from Hodder's education book written by Tom Duncan and Heather Kennett. This is a very popular book, and here the pressure is defined as a force per unit area and is calculated from pressure is equal to force per divided by area. So force per unit area is the basic definition of pressure. So, and the unit of pressure is Pascal and is written as PA, and 1 Pascal is equals to 1 Newton per square meter. So 1 Pascal is equal to 1 Newton meter square, and a Pascal is a very small unit of pressure and can be understand from this simple example. And an apple in our hand exerts about 1000 Pascal pressure. So similarly, the pressure can also be understood through this reasoning. Why tractors with wide wheel move easily over soft ground? So the greater the area over which a force acts, the less the pressure it will exert. That is why a tractor with wide wheels can move over soft ground, while the other vehicles with narrow tire can't drive well in a soft ground, because that exerts high pressure while tractor exerts low pressure. And the pressure is large when the area is small, and this is why the nails are made with sharp points, so it can penetrate any place because of low area, so high pressure will be applied. Now put this into practice. Page 78. A rectangular box has a width of 2 meter and a height of 5 meter and a depth of 2 meter, like this. Here we have 2 meter and 2 meter depth, and a height is 5 meter. So the area at the base, at the top and the base is same, and here we can multiply the width with the depth. So this is the base area, and the base area is 4 meter square. So base area 4 meter square, and the one of the side of the box, here we have the height is 5 meter, this is 2 meter. So this face, one side is 10 meter square. So 5 into 2 meter is 10 meter square. So part 1 is 4 meter square, while the part B is 10 meter square. So this is 1A and 1B problems. We have, if the box has a weight of 80 Newton, and calculate the pressure on the base of the box. So the base of the box area is 4 meter square, so 80 Newton divided by 4 meter square is equal to 20 Newton meter square. So the pressure at the base of the box is this 20 Newton square. The pressure will exert on the side. If the box is tilted toward the side, one of the side, then the base area becomes 10 meter square, like this. So when 80 Newton divided by 10 meter square, it will give the pressure of 8 newtons per meter square. So because area is wider, so the pressure will be lower. In question number 2, calculate the pressure on the surface when a force of 50 Newton act on the area. Area is 2 meter square, 100 meter square, or 0.5 meter square. The case 1, 2 meter square, so the 50 Newton divided by 2 meter square is 25 Newton per meter square is the pressure. In second case, 100 meter square, 50 Newton divided by 100 meter square is equal to 0.5 Newton meter square. While in the third case, 0.5 meter square, so 50 Newton divided by 0.5 meter square is equal to 100 Newton meter square. So we can see that the force is same while the area is different. So with a smallest area gives a highest pressure in a case number 3. In the part B, a pressure of 10 Pascal acts on area of 3 meter square. What is the force acting on the area? So the pressure and area is given, so pressure is equal to force upon area, so F is equal to PA, and P is 10 Pascal while area is 3 meter square, so 10 Newton meter square into 3 meters square. So this meter square will cancel this meter square, and 10 into 3 is 30 Newton. So the force is 30 Newton. In a liquid pressure, Pressure in a liquid increases with depth. So in this figure 1.83, we can see that the pressure at the bottom is highest, while in the mid is moderate, and at the top is very low pressure. We can see here pressure at one depth act equally in all directions. Here the depth, the hole is at the same point, the same depth level, so we can see that the pressure is same. A liquid find its own level. So in a U-tube of figure 1.84a, the liquid pressure at the foot of P is greater. Here at this point is greater, while at Q is pressure is lower. Because the column height of this P tube is larger than this Q tube, so this will have a higher pressure. When the clip is open, the liquid flows from this high pressure to the low pressure until the pressure and the levels are equalized. So it will move this way. Here the cross section area is high, so the pressure will be low in this case. Even though this mass is volume is high, even then this pressure is low because of the cross sectional area. In figure 1.84b, this is B, the liquid at the same level in each tube, and confirm that the pressure at the foot of the liquid column depends only on the vertical depths. So the shapes are different. Here this is wider, this is spherical shape here, and tube shape, flask shaped, while this is a tilted shape, but the level is at the same level irrespective of the shape. So confirm that the pressure at the foot of a liquid column depends on the vertical depth of the liquid and not on the tube width or shape. So this is confirmed through this. And pressure depends on the density of the liquid. So the denser the liquid, the greater the pressure at any given depth. So pressure is equal to density of the fluid or liquid into acceleration due to gravity or gravitational field strength into height. So if these are constants, then this pressure is directly proportional to the density of the fluid or liquid. And water supply system, a town water supply systems after comes from reservoir on a high ground. This is high reservoir. From this the water level comes to the different levels. So this can be lifted easily because this is at a very high head, while for this transfer of reservoir from this bottom to the top needs a pump. So because this elevation is even higher than this reservoir, plus the bending or pressure drops in the line or tubes or due to various bends is also causing a pressure drops. So in order to get the water at different levels, this water has to lift at the high reservoir tank in the building, so that everywhere the water supply can be provided as per requirement. The lower the place supply, the greater the pressure, water pressure. The dam must be thicker at the bottom than at the top due to the water pressure at the bottom. Pressure head, the dam bottom should be thicker because the water head exerts pressure at the bottom, at the maximum pressure at the bottom. So the bottom of the reservoir should be thicker. Test yourself, page 79. Why is the pump needed in a high-rise building? Shown in figure 1.85. In a very tall building, it may be necessary to pump the water to a larger overhead tank in a roof because the height of the roof above the top level of the reservoir and pressure drops occur in the piping roof due to various bends. So due to various bends, the pressure drops. Secondly, this reservoir, the height of this upper tank is even higher than this reservoir. So there are two main reasons as discussed here. And why are the dam walls built to be thicker at the bottom? Because the dam must be thicker at the bottom than at the top due to the larger water pressure at the bottom. So the high pressure exerts on at the bottom, so it should be, so high pressure exerts, so bottom should be thicker so it can sustain this high pressure. Now put this into practice. In a hydraulic jack, a force of 20 Newton is applied to a piston of 0.1 meter square. Calculate the load which can be lifted by a second piston of area 1.5 meter square. So force is 20 Newton, area is 0.1 meter square. Now load has to operate and the area of that load is 1.5 meter square. So pressure is equal to, the pressure will be same at both sides. So here we have pressure 1 and pressure 2 and both pressures are same. So areas are different. So the pressure act on a second piston of a larger area introducing an upward force. So F is equal to pressure into area. So pressure is written as this F upon A and area is this is capital A. So F upon A is 20 Newton, 0.1 meter square and multiplied by this 1.5 meter square. This F, capital F and A and small f and small a has the same relation. So this A should be here, F upon A, capital F upon capital A is equals to F upon A. So this in the denominator, this A can be shifted here and F upon A into A, 20 newtons per meter, 0.1 meter square, and this is 1.5 meter square, meter square we cancel, and here this is 15 into 20 is 300 newtons. By dividing this it becomes 15 and this 300 newtons. A force of 20 newton could be used to lift a weight of 300 newton. The hydraulic system multiplies force to many times. Here in this case it is 15 times. So in a hydraulic jack, a load of 70 Newton is required to be lifted on an area of 1 meter square. Calculate the force that must be applied to a piston of area 0.1 m square to lift the load. So we have to lift 70 Newton while the area of that load side piston is 1 meter square, and we have to find the force that has to applied to lift this force, and while the area of that piston is 0.1 meter square. So F is equal to F upon small a into A, and this is small f. We have to find this small f. So small f is equal to F into small a upon capital A. Here F is 70 newtons, A is 0.1 meter square, while this A is 1 meter square. So 7 Newton has to be applied. So this F is 7 Newton. The force of 7 Newton on the piston area 0.1 m square could lift the load of 70 Newton at area 1 meter square. Here the multiplying factor of force is 10 times in this case. Now the property of a liquid on which a hydraulic jack relies. Liquids are almost incompressible. The volume cannot be reduced or squeezed, and they pass on any pressure applied to them. The hydraulic jack works on this principle. So hydraulic pressure, because of incompressibility of the liquid, so it works on this principle. A hydraulic jack has a platform on the top of a piston B and is used in a garage to lift a car. So here we have a small area, cross-sectional area. Here we apply a piston and this lifts a heavy weight. So here we applied a small force in this area and this exerts a high force here because of this larger area, and this way a hydraulic jack works. Both valves open and only to the right they allow B to be raised a long way when piston A moves up and down repeatedly. By pressing it, it will lift up. And expression for liquid pressure. In designing a dam, an engineer has to calculate the pressure at various depth below the water surface. The pressure increases with depth and density. So an expression for the change in pressure at a depth below the surface of a liquid of density can be found by considering a horizontal area. In this figure, this is the base area and this is the height. So at various depth level, this pressure will be different. So the volume of the liquid column is delta H into A. So this is cross-sectional area multiplied by the depth level. So this is volume, and volume multiplied by density is called mass. So mass is equal to density into volume. So density into volume is mass, and mass multiplied by gravitational field strength is called weight. So weight of the liquid column is rho delta HA and this G. So rho GHA, and when this is A is area, cross-sectional area, and this is weight is basically the force. It is measured in Newton, and force on area becomes the weight on that area. So we divide by G to get the pressure. So the pressure due to the liquid column is force per area, so we divide by this area, and this A will cancel, and rho G delta H. So the pressure becomes rho G H delta H, and delta P is the change in the pressure beneath the surface of the liquid at depth delta G due to the weight of the liquid of density rho, and G is the gravitational field strength. So this rho is density and G is the gravitational field strength. This can be written in words that change in pressure is equal to density, gravitational field strength, and change in height. This expression is written as this. So test yourself. Calculate the increase in pressure at a depth of 2 meters below the surface of water of density 100 kilograms per meter cube. Increase in pressure is delta P at the depth of 2 meters. Water density is this much, so delta P is equal to rho GH. This is 1000 kilogram meter cube, 9.8 Newton per kilogram into 2 meter height. So this much is pressure, 19600 Newton meters square. Calculate the depth of water of density given as 1020 kilogram per meter cube, where the pressure is 3 into 10 to the power 6 Pascal. The depth of water is delta H. Rho is 1020 kilograms per meter cube, while the pressure is 3 into 10 to the power 6 Pascal. So delta P is equal to rho G delta H, and we have to find the delta H, depth of the water. So delta H is equal to delta P upon rho G, and delta P is given as 3 into 10 to the power 6 Pascal, and density is 1020 kilograms per meter cube, and G is 9.8 newtons per kilogram, and on simplification we obtained the delta H is equal to 300 meters. So this much pressure will be exerted at the level of 300 meters depth level of this liquid, the water level. In the next session we will discuss this exam style question.